I'm Matthew Addison. I'm part of the speed team, which consists of myself and Benjamin Enos and Michael Hansen. Today I'm going to go over an outline of the waste management mixer aerator system, and I'm going to review the steady-state operating curves, the FOPD modeling of the unit step, and the frequency response modeling. This is a diagram of our whole system. It's powered by this motor right here, which is what we're varying our power input. It then goes into a 101 gearbox gear reduction to the mixer, which is in the tank of the wastewater. The mixer, the idea of it is as it spins, it mixes in oxygen with the wastewater to stimulate bacteria growth, to help break down the wastewater. This is a block diagram of the aerator user interface. It's simple. It doesn't really change throughout all the experiments, as you'll see. The operator inputs is the only thing that changes what is required depending on the type of experiment. In the first case, for the steady-state operating curve, it was just a power input and a length of experimental time in which the motor ran. As you can see right here in this plot of our data, this is for the up to the 350 range, RPM range, for a 20% power input. And you can see the averages and the standard deviation calculated for each one. This is a combination of back when our group was only 2 people. We had our upper range and our lower range, and this formula right here is an easy way to predict several different outputs depending on your input percentages for any sort of steady-state operating curve experiment that you would run on the system. Again, this is our block diagram, but you can see that the only thing changes whenever you do the unit step response is the percent input, then the percent in power that you're going to step at a certain period of time, which in our case was 5 seconds, and then our total experiment run time. This is a plot of the whole system I just explained for the unit step, where we started at 10% and I stepped up 10% to 20%. And you can see the output RPMs of our motor as it changed in accordance with the power percent step. We were then tasked with fitting the FOPDT model to the actual experimental data. The FOPDT model, the purpose would be to, like the steady-state operating curve, to predict the actual behavior of what the motor should see, assuming no sort of resistance or no sort of external inhibitors to the actual performance of the aeration system. In this case, you can see that the motor, it took a longer amount of time before it actually started to reach higher RPMs. This could be due to the actual resistance from spinning a mixer in the wastewater, or temperatures, or there could be infinitely large number of variables. This is a bar chart of the low range RPM back when it was still only 2 people, and we did the low range of 100 to 600 RPM, and it's a comparison between the step up and down of the gain, the dead time, and the time constant. As you can see, the dead time was so small, it was about 0.02. It won't even show up on here, but they were virtually the same, as well as the time constant. There was very little change. I'm pretty sure this was 0.021 and 0.023. But as you can see, the gain, it was much more obvious at 16 and 16.6, I believe. And it's the same sort of behavior for our high range of 1100 to 1600 RPM. The same sort of difference in the high gain values, but our dead time and time constants were again very small, with very little difference between the two. All of the previous experimental data for the unit step was to lead up in a comparison between how the system reacts from a frequency response to a actual unit step response, which is just a power variance and what the motor is seeing. All you're doing is adjusting the amount of power, and in a different fashion, where the step response only increased by a certain amount one time. The frequency response allows for a constant fluctuation in the power input. And in this case, you input the amplitude, the frequency, and the total runtime. This is an example of a plot of our amplitude ratio and the fit that we used in order to calculate the FU, the K, and the 1 over KCU. It follows fairly smooth slope on the log-log, or the log-log plot. The phase angle was on the semi-log plot, where the graduation for the actual phase angle was in a standard form, where the frequency itself was log in order to force the actual curve. This is the model overlaid on these points, which were the data from the amplitude ratio for the frequency range that we performed. And it's also difficult to see, but the error bars are there, but they were very low error for our amplitude ratio. You can't even see this one had the largest error, and you can just see the edges of the bar. But this was the actual model that it was supposed to follow. As you can see, it's fairly close. It's almost collinear until about right here. I believe that if you continue to run the experiment, that this gap would grow larger and larger as it got closer to the higher, which was 6.5 hertz. This is a comparison between our step response and frequency response of the motor for the low range. We were only able to really compare the low range and the high range, considering that before, when it was only 2 people, we only had unit step response data for just the low range for our system. So when it was compared, the frequency response, the gain was much lower than the actual step response, where the dead time in the tower, again, the numerical values were so small that it was almost impossible to determine or validate any sort of real difference. You can see in the high range too, the frequency response was, the gain was actually higher this time than the step response, and the difference was larger than it was for just the step response when you compare the step up and down. And the dead time and the time constant again remained, the difference remained relatively negligible. In a total summary, when comparing the two, as I said before, the dead time and the time constant values were, the difference was very negligible. There was hardly any change whatsoever, but the differences in the gain were much higher. There was a 9% gain for the frequency response in the high range, and a 39% less gain for frequency response in low range. The theory behind that is that in the high range, the motor is able to react much more quickly because it's receiving much more power, in which case the gains would be much closer. Whereas in the frequency response for a low range amount of power, or the low range spinning, it's difficult to get the motor spinning up quick enough with said resistance. So a frequency response, which is fluctuating much more often than the unit step, would have less gain.